Hey there, and welcome to The Explainer. Today, we're going to pull back the curtain on a hidden world that exists on pretty much every surface you touch, from your phone screen to a car engine. We're talking about the science and, honestly, the art of creating perfectly smooth surfaces. And trust me, it's way more complex and fascinating than you might think.
So, let's start with a basic question. What does it even mean for a surface to be perfect? I mean, to our eyes, the screen on your phone probably looks totally flawless, right? But if you were to zoom in with a microscope, you'd see this whole landscape of tiny little peaks and valleys. And believe it or not, controlling that microscopic landscape, well, that's the entire game.
And the way we measure this is with a key metric called surface roughness, or you'll see it written as RA. It's really just the average height difference between all those tiny peaks and valleys. So the lower the RA number, the smoother the surface. And in the world of high-precision manufacturing, that number is everything. It's the holy grail.
Okay, so here's our game plan for this lecture note. First, we'll talk about why this whole pursuit of perfection even matters. Then, we'll look at the incredible toolkit engineers are using to plan for it. After that, we'll see what happens when that perfect plan crashes into reality. And finally, we'll look at how AI is shaping a future that is completely adaptive. So, let's kick it off with part 1, the pursuit of perfection. You might be wondering, why on earth would we obsess over microscopic bumps on a piece of metal? Well, it turns out that a flawless finish is critical for reasons that go way, way beyond just looking pretty. So why is it so critical? Think about it. A smoother surface means less friction and less wear and tear. That directly translates to products that last longer and are way more durable. It boosts the mechanical integrity of a part, making it stronger and more efficient. And when you're talking about something like a turbine blade in a jet engine or a biomedical implant, getting the surface finish right isn't just a bonus, it is an absolute non-negotiable requirement for safety and performance. Which brings us right to our second section, the optimization toolkit. I want you to think of this as the planning phase. It's like being a master chef. Before a single piece of metal even gets cut, engineers are using these incredibly sophisticated tools to craft the perfect recipe for getting that ideal surface. And what's really cool is what's actually in this toolkit. You've got the more traditional statistical methods like RSM, which are fantastic for modeling physical things, like the exact shape of the cutting tool. But then you get into the AI-driven approaches, and this is where things get wild. One team used a combo of artificial neural networks and genetic algorithms, and get this, they were able to predict surface roughness with an error rate of less than 2%. That is just incredibly accurate. And then, taking it even further, another team used a real-time AI model that can learn from one machine and then instantly apply that knowledge to a totally different one. It's a concept called transfer learning, and it's a massive time saver, a total game changer. And, this quote from the research just hits the nail on the head. We are fundamentally shifting away from static, rigid blueprints. Instead, we're building intelligent, dynamic systems that can actually predict and adjust before a problem even has a chance to happen. It's a massive leap forward. So, you've done it. You have this perfect plan, this flawless recipe, all modeled and predicted down to the finest detail by super powerful computers. I mean, what could possibly go wrong? Well, that's what brings us to section 3, the quest for consistency. This is the moment where that pristine, perfect digital model smashes head-on into the messy, unpredictable, and chaotic physical world of manufacturing. Because in the real world, tools wear down, temperatures spike and drop, the materials themselves aren't always perfectly uniform, and any one of these variables can take that perfect plan and just toss it right out the window. Just take tool wear, for example. Research has found this fascinating 3-phase pattern. First, you have a stable phase where the surface roughness is nice and consistent. Then you get gradual wear where the surface starts getting a little bit rougher. But here's the really weird, counterintuitive part. Right before the tool fails completely and chips, the surface can suddenly get smoother. It's this bizarre little warning sign, and being able to spot that in real time is absolutely vital if you want to avoid making a whole batch of bad parts. So, how do you manage all this chaos? Well, a huge part of the strategy is just controlling the environment. Old-school dry machining creates a ton of heat, and that causes all sorts of problems. But newer techniques can dramatically stabilize the cutting temperature. Things like minimum quantity lubrication, which is like a fine mist of oil, or cryogenic machining, which literally uses liquid nitrogen to supercool the tool. Both of these can slash tool wear, and the result is a much more consistent, much higher quality surface finish.
And all of this brings us to the final and I think most exciting piece of this whole puzzle. The future is adaptive. This is where we finally merge that pristine digital plan with the messy physical reality, using technology to bridge that gap once and for all. So how does it all come together? Essentially, AI acts as the central brain of the entire operation. It's constantly taking in live sensor data, vibration, temperature, even sound, to predict what the surface quality will be in real time. Then it uses adaptive control to automatically tweak things like cutting speed to compensate for tool wear as it's happening. And with transfer learning, that AI can get smart on one machine and then transfer all that knowledge to another one. It's the ultimate feedback loop, creating a system that is truly self-correcting. So if we go back to our chef analogy one last time, this is the difference between a cook who just blindly follows a recipe no matter what, and a master chef who is constantly tasting the dish, adjusting the seasonings, and perfecting it as they cook. That is the massive leap we're talking about with adaptive manufacturing. So let's wrap this all up. What are the key takeaways from our little lecture on the modern approach to creating a perfect surface? Okay. First, remember that getting a great surface finish is a battle you have to fight on two fronts. You need amazing optimization, which is the plan, and you need relentless consistency, which is the execution. Second, those advanced predictive models give us the power to create incredibly accurate plans. Third, you can never, ever ignore reality. Factors like tool wear and heat have to be actively managed. And finally, the future. The end goal of all of this is fully adaptive, AI-driven control, where the machine itself is ensuring its own perfection. And that leaves us with one final thought to chew on. As these machines get smarter and smarter, and they become more capable of self-correction, essentially removing human error from the equation, what's going to be the next big challenge? What is the next frontier in our quest for perfect manufacturing quality? Thanks for tuning in.